I'm not going to review the paper, but I'm going to give you an example of a conference presentation, a paper that I've written. I've given the presentation, but I haven't looked at this recently, so let's see how this goes. Although I like this paper. So this was the work that we did at Microsoft Research with an ETH alumnus, actually. Thomas is from Switzerland, and he was my, not office mate, but we were in adjacent offices. And Thomas did his PhD, actually all his degrees here at ETH. And we worked together to write this paper. So I'll give you a conference talk, basically. Of course, maybe I'll interject in between and say, make jokes or something. But you can ask questions and analyze what I described, as opposed to me analyzing the paper itself, right? And I'm going to use exactly the same slides that I used about 10 years ago. This was in 2008 in ISCA in China, in Beijing. Okay, so I'll talk about parallelism-aware batch scheduling, enhancing both performance and fairness of shared DRAM systems. This is the outline. Basically, I'll give background and goal first, and then we'll take it from there. So DRAM system looks like this at some abstraction level. Basically, you have banks that consist of two-dimensional arrays of columns and rows, and data can be accessed only from the row buffer. And each bank has a row buffer, and you get bank-level parallelism by overlapping accesses to different banks. And a DRAM controller orchestrates that bank-level parallelism. Because of this structure of the DRAM controller uses a policy prioritization order that's called first ready, first come, first serve. A row buffer, an access to a row that's already in the row buffer takes much shorter than an access to a row that's not in the row buffer. As a result, it prioritizes the accesses that go into the that hit in the row buffer. Otherwise, it prioritizes the accesses that are older than others. So this is the policy that's employed today. The goal is to maximize DRAM throughput because the access to the row buffer is much faster than an access to some row that's not in the row buffer. And oldest first, the idea is to have some sort of fairness. Okay, in multi-core systems, so this is the design of the DRAM controller that carries through from single-core systems. In multi-core systems, we have the same DRAM structure over here, a memory controller, but the core structure is changing. We have many more cores now, and some sort of cache structure. But the key over here is that you have a shared memory system that consists of DRAM. And when these cores access DRAM, their requests interfere in the memory controller. Memory controller has a choice to prioritize one over the other. So it turns out this is an important problem. Basically, threads delay each other by causing resource contention. Sorry, I had to switch to something. Yeah, by causing resource contention. And this contention happens in the bus, in the bank, in the row buffer. And we've shown that in some of our previous papers that was published and presented at Micro, stall time fair memory scheduling. In this work, we also show that threads can also destroy each other's bank-level parallelism. When otherwise parallel requests can become serialized, because if a thread is running alone, its requests are serviced in parallel. But when some other thread's requests come in, both of those threads' requests may be serialized. And existing DRAM schedulers are unaware of this interference. They simply aim to maximize DRAM throughput, as I described. They use the FRF-CFS policy that tries to maximize DRAM throughput. They're thread unaware, and as a result, they're thread unfair, because they have no intent to service each thread's requests in parallel today. So FRF-CFS policy, as I said, it's row hit first and then oldest first. It unfairly prioritizes threads that have high row buffer locality. And it also unfairly prioritizes threads that are older, whose requests appear older, memory-intensive threads. So this is one example of the consequences of uncontrolled inter-thread interference in DRAM. These are results from simulation. These are 4 different workloads. We simulated them running together and running alone, and we compared the performance they get, a slowdown that they experience, compared to when they run alone on the same system. And DRAM is the only shared resource over here. One application, very streaming, slows down by only 5%. Another application slows down by about 8x. And some of these applications may have real-time requirements. For example, if you're doing video decoding and you don't want frames to be skipping, right? So there are many issues related to this uncontrolled inter-thread interference in the DRAM system. You get unfair slowdown of different threads. People may be discomfortable. You get system performance loss because this core may be making progress, but it's very heavily memory intensive. So it's not making a lot of progress, even though it is getting its request serviced. But this core, it's not that memory intensive. It's just waiting for memory requests to be serviced for a long time. So exactly, you would like to enable many cores to make progress, but this is doing exactly the opposite. As a result, system performance is not is reducing. And you get vulnerability of denial of service, as we've discussed in Unix security last year. I'm not going to talk about that. Somebody will present that paper here later. And you have the inability to enforce system-level thread priorities, because if you change the thread priority over here, oh, I already said this, I didn't animate, but if you change the priority over here, this memory performance hog doesn't change, basically. You have 4 cores, and all threads are scheduled, and operating system basically says, good luck, run together. It's not going to deschedule some of the applications. Okay, so there are a lot of issues, basically. As a result, you have an uncontrollable system. So our goal in this work is to control inter-thread interference in DRAM and design a shared across multiple cores, shared DRAM scheduler that provides 3 characteristics. It provides high system performance by preserving each thread's DRAM bank level parallelism. It provides fairness to threads sharing the DRAM system by trying to equalize memory slowdowns of equal priority threads. I'll talk about that. It's controllable and configurable. It enables different service levels for threads with different priorities, because you don't want perfect fairness all the time. Sometimes you care about one thread more than others, right? So let's take a look at this DRAM bank level parallelism. That's one of the key contributions of the paper. And our motivation was that, actually. So what we observed is that when you're running multiple applications together, you can destroy the intra-thread bank level parallelism. So why is this important? Processors are designed to tolerate the latency of memory requests by generating multiple outstanding misses. This is the notion of memory level parallelism. You can generate multiple requests, and there are multiple ways of doing it. You could use out-of-order execution, non-blocking caches, run-ahead execution. You can have multiple requests in flight. And this has been a very useful thing to improve performance. Out-of-order processors have been high performance because you can service these requests in parallel. Now, this is effective only if the DRAM controller actually services the multiple requests in parallel in DRAM banks, assuming in the first place that these requests go to the DRAM banks in parallel. So in multi-core systems, multiple threads share the DRAM controllers, and the DRAM controllers are not aware of a thread's memory level parallelism. As a result, we found out that it can service each thread's outstanding requests serially and not in parallel. And this leads to a performance loss in the thread as well as the entire system. So let's take a look at it pictorially. I'm going to show you what happens when you have a single thread executing and with a memory that has 2 banks. So the thread computes, then it gets 2 DRAM requests. It sends their request to the memory controller. Those requests happen to map to different banks, which is good. And the memory controller starts servicing this request first. The thread stalls, and the memory controller starts servicing this next request next in the next cycle. These 2 requests are being serviced in parallel. And while they're being serviced in parallel, the thread stalls. After some point, this is done. It gets sent back to the core. The core still stalls because it needs the other request also. And then this request is done. The data is sent back to the core, and now the core can compute. So what happened here is the thread had 2 requests. They went to 2 different banks, but the bank access latencies of the 2 requests are overlapped. As a result, the thread stalls approximately for 1 bank access latency. There are other access latencies that I'm not showing here, but the bank access latency is a dominant part of the DRAM access latency. So this is beautiful because you parallelized the requests, and you stalled only once per 2 requests as opposed to stalling once per each request. Now let's see what happens if you have if you run these 2 threads on an existing system with a row hit first scheduler, like we discussed, or a scheduler that's unaware of interference. Let's assume you have the same thread copied, but it's doing something different. They both generate 2 DRAM requests, and these requests happen to arrive at the memory controller like this, in this order. And let's assume the memory controller services the requests in the arrival order. It takes first thread A's request to bank 0, schedules it. Both threads stall. It takes then thread B's request to bank 1 and schedules it. Both these requests get serviced in parallel, and during that time, both threads stall. Then this request is done. The data gets back to the core. The memory controller takes the next request, schedules it to bank 0. Then this request gets done. The data gets sent back to the core. And the memory controller schedules this last request to this bank. Even though first data items have arrived, these threads keep stalling because they need 2 requests to be serviced as opposed to 1 request to progress, right? So both of these threads stall until these last requests get serviced. And after that, the threads can compute. So what happened here is each thread had 2 requests to different banks, but their requests got serialized because the memory controller actually was not aware that these threads had memory level parallelism. The bank access latency of each thread was serialized. Each thread stalled for approximately 2 bank access latencies, as opposed to 1 in the previous example that I showed you. So the key question we asked is, can we do better? In this case, if you had an intelligent memory scheduler, it would recognize that these requests can be serviced in parallel, and it would do something better. And something better is this, basically. The same scenario, requests come in the same order as here into the memory controller. And the memory controller is parallelism aware. What it does is it takes thread A's request to bank 0, schedules it. Now in the next thing, it doesn't take the next request, but it asks the question, is there another request from thread A to some other bank? And it finds it, the last request, and schedules it. Now both threads stall while these 2 requests are being serviced. Now the first request is done. The memory controller takes the thread B's request to bank 0, schedules it. And then the next request is done. The memory controller, of course, sends the data back, and takes thread B's request and schedules it. Now what happened here was, because we first serviced thread A's request in parallel, thread A can continue computation at this point when both of its data requests come back from memory. Thread B continues to stall until the last 2 requests are done. So if you look over here, compared to the baseline scheduler, we saved cycles in this particular thread because we were aware of the parallelism of the requests. So if you look at this picture, both threads have their requests to different banks serviced in parallel. No problem. We didn't break the parallelism. We didn't serialize any of the requests. We just ensured that this thread's requests were serviced first and this thread's requests were serviced next. As a result, you save overall cycles. And if you look at the average stall time, here you get about 1.5 bank access latencies. Okay, so that's the key idea of parallelism over batch scheduling. Now let's see how we can actually implement it. So there are 2 principles behind this, and the first principle I just gave you, it's called parallelism awareness. This idea can be summarized as you schedule requests from a thread to different banks back to back. This preserves each thread banked parallelism. But this can cause starvation. And as a result, the second principle we employ is batching, because it can cause starvation because you may actually service this thread's request and the thread keeps generating requests. As a result, you would be prioritizing that thread only. To ensure you eliminate starvation, we have the second principle, request batching. The idea is to group a fixed number of oldest requests from each thread into a batch and service that batch before all other requests. That way you ensure that nobody is starved and there's some sort of fairness in the system. And you form a new batch when the current one is done. This eliminates starvation and provides fairness, and this allows parallelism awareness within a batch. So within a batch, you can do parallelism awareness without consideration for starvation. So let's take a look at it. Look at both of these principles. So basically, threads generate requests. In this case, 4 threads. Each has 2 requests to 2 different banks. We form a batch. At some point, we declare the batch. We're going to talk about that. And within the batch, we basically follow the parallelism awareness principle. We take thread 0's requests first, schedule them, so parallelism is preserved. Thread 2 keeps generating requests. As you can see, we don't include them in the batch, because if we include them in the batch, we may be starving others. And then thread 1's requests are served, and then thread 2's requests are served, and then thread 3's requests are served, and you get good parallelism, and then you form a new batch after that. That's the idea, basically. It's very simple. So how do you do these 2 components? How do you design them? Request batching and within batch scheduling. Request batching is simple. Each memory request has a bit. It's called a marked bit. And basically, batch formation happens when the previous batch is done. There are no marked requests in the system. And the memory controller goes through the request queues and marks up to some number of requests, number of oldest requests per bank for each thread. This is called marking cap. Of course, this enables a trade-off now, which we're going to discuss later. Marked requests constitute the batch, and marked requests are prioritized over unmarked ones. That ensures that there is no reordering of requests across the batches, no starvation, high fairness. High fairness, we'll get back to that. How do you prioritize requests within a batch? That's the next question, now that we've formed the batch. There are many other ways of forming the batch, but we're limiting ourselves to this one for now. So within batch scheduling, it can actually use any existing DRAM policy, DRAM scheduling policy. It could use FRF-CFS, as we've discussed earlier. This exploits the row buffer locality. But we also want to preserve intra-thread bank parallelism, service each thread's request back to back. So the idea that we propose is to have the scheduler compute a ranking of threads when the batch is formed. And remember, we want to maximize parallelism, we want parallelism awareness, and we want to prioritize, we want to send the request of a thread back to back. So you form a ranking, and you follow that ranking to schedule the requests. Higher ranked threads are prioritized over low ranked ones, and this improves the likelihood that requests from a thread are serviced in parallel by different banks, because different threads are prioritized in the same order across all of the banks. Okay, so now the next question is, of course, okay, ranking is good, it preserves parallelism awareness maybe, but how do you form this ranking? It affects both throughput and fairness, that's why this is important, and our goal is twofold. We want to maximize the system throughput with parallelism awareness, as well as enabling the cores to make progress, and we want to minimize unfairness. And unfairness, in our case, in this case, our definition is to equalize the slowdown of the threads. All else being equal, this is not a bad unfairness definition, but of course, fairness is a huge concept, and there are many, many definitions of it. We're going to use this one. So if you want to it turns out both of these point to a similar policy. The first, if you want to maximize the system throughput, you want to minimize the average stall times of the thread within the batch. You want to minimize the red parts, basically, on average. The green parts you want to maximize. If you want to minimize unfairness, you really want to service the threads with inherently low stall time early in the batch. So if a thread stalls a little bit, you want to, more than another thread, you would like to prioritize that thread. Because let's assume that you have a memory-intensive thread and a memory-non-intensive thread. Memory-non-intensive thread initially has a low stall time to begin with. Memory-intensive thread has a very high stall time for memory. Let's assume that both of them are impacted by equal amounts. That equal amount affects the memory non-intensive thread much worse, because it has a little stall time. It gets, let's say, its stall time gets doubled. Whereas if you're memory intensive to begin with, if you just get the same amount of stall, just a little bit more stall time, it doesn't matter, because you're so delayed because of memory. So that's the insight. Delaying memory non-intensive threads is not good for fairness because they get impacted a lot. So it turns out shortest stall time first, or shortest job first ranking, maximize the throughput. Actually, this is proven to be optimal in the case where you have a single bank without a row buffer. It's done in factory production, actually. I'm not going to go through that. In this case, we cannot claim any optimality in system throughput because we have a very different system, many banks, many row buffers. But basically the idea is the controller estimates each thread's stall time within the batch and ranks the threads with shorter stall time higher. So let's take a look at an example of this to motivate it. Basically, we actually have two metrics: maximum number of mark requests to any bank for a given thread. This is called max bank load. And we rank the thread with lower max bank load higher because this approximates low stall time. And as a tiebreaker, we use total number of mark requests. This is called total load. If there's a tie, we rank the thread with lower total load higher. Basically, remember, we're trying to approximate stall time. If a thread has small stall time to begin with, we're going to prioritize that. If a thread has lots of stall time to begin with, we're going to deprioritize that within that batch. You may think this is unfair. Yes, it's unfair within the batch potentially. It can starve, if you do it indefinitely, it can starve threads that have a lot of requests. But remember the batching boundary. We're doing this only within a batch. Okay, so let's take a look at this is the batch. And now we have different threads. I'm going to ignore the row buffer here, but the paper is an example with the row buffer. And these threads have different number of requests. Let's compute these two metrics for these threads. Thread 0 has only one request maximum to any bank, so its max bank load is 1. Its total load is 3, so it has 3 requests across all of the banks. Thread 1, its max bank load is 2 because the maximum number of requests it has to any bank is 2. Its total load is 4. Thread 2, its max bank load is 2 because the maximum number of requests it has to any bank is 2, to bank 1 and bank 2. Its total load is 6. And thread 3 is the heaviest one. It has the highest stall time to begin with. Basically, it has 5 requests to bank 3, so its max bank load is 5, and its total load is 9. Now we can form a ranking based on our principles, right? Basically, it says shortest max bank load first. It's ranked the highest. And then we have a tiebreaker here. Thread 1 is ranked higher than thread 2 because thread 2 is more intensive, as you can see, and thread 3 is ranked the lowest. And we're going to use this ordering to schedule the requests. So let's take a look at the baseline scheduling order. Let's assume this is the arrival order. It's first come, first serve. If you use this scheduling order, I'm going to assign some time units. Assume that each request takes 1 bank access latency over here. Let's take a look at how long it takes for each thread to finish its request. Thread 0, basically this is the order of requests, and thread 0's last request gets serviced after 4 time units. So its stall time is 4. Thread 1's last request gets serviced after 4 time units also. Its stall time is 4. Thread 2's last request gets serviced after 5 time units. Its stall time is 5. Thread 3's last request gets serviced after 7 time units, as you can see over here. So it stalls for 7. And on average, threads stall for 5 bank access latencies. Now let's look at our parallelism-aware batch scheduling for this batch. Remember the ranking. We're going to prioritize T0 over T1 over T2 over T3. So the first memory controller is going to prioritize T0's requests. Its parallelism is going to be preserved. Its last request is serviced after 1 bank access latency. Next, of course, this is happening while things are running, so it's not next really. The memory controller is taking thread 1's request and scheduling it to bank 0. So thread 1's requests are scheduled like this. And its last request is serviced after 2 bank access latency, so it stalls for 2 units. Thread 2's request gets scheduled like this next, so it stalls for 4 units. And thread 3's request gets scheduled like this, so it stalls for 7 time units. So within this batch, as you can see, the average bank access latency is 3.5 for each thread, for on average across all threads. So we have about a 30% reduction in the average stall time of the threads. And it looks nice, as you can see, the parallelism is preserved for each thread as much as possible, as opposed to this order where parallelism is not preserved and you get a lot of serialization, potentially. Of course, it's a nice example, right? I picked this example to motivate the mechanism. But the paper actually has another example with the row buffer locality. Okay. So basically, how do you actually design the policy right now? So you need a scheduling policy. We want to keep it simple. So we're going to modify the baseline FRF-CFS scheduling policy in 2 ways. This is FRF-CFS priority order 1, FRF-CFS priority order 2. I said that already. So we're going to add batching. Mark requests are prioritized over everything else. That provides starvation freedom. FRF-CFS is not starvation free to begin with. And then this is parallelism awareness. Now the paper has a lot of detail on the ordering of these. It turns out if you want true parallelism awareness, you want higher ranked threads first scheduled, just like I described. But parallelism and locality go against each other because there's also a row buffer locality, which is important in scheduling. And empirically, we found out that this policy works better than the other ordering, where higher ranked thread is ordered. Basically, higher ranked thread first is the higher ordering requirement compared to row hit first request. So there are 3 properties of this. It exploits both row buffer locality and intra-thread bank parallelism with the rules 2 and 3. Maybe not the best of both, so there's a room for improvement. It's work conserving. Basically, this means that it doesn't waste bandwidth. It services unmarked requests to banks without marked requests. So it's a prioritization order. If a bank doesn't have a marked request, you go to the next priority level. If a bank doesn't have a row hit request, you go to the next priority level. Marking cap is important. This is the cap that decides how big is your batch. If you actually have a small cap, your batch is small, which means that the ability to exploit the row buffer locality within a smaller number of requests is lower. If your cap is too large, now you starve some of the threads for longer. For example, a memory non-intensive thread, it cannot insert its request into a batch. It needs to wait until the next batch, but it needs to wait for many more requests if your batch is too large. So this is important, and this is analyzed in the paper in detail. And there are many more trade-offs that are analyzed in the paper also. So what is the hardware cost of this? It turns out there's analysis in the paper. It's less than 1.5 kilobyte storage cost with a relatively large system, 8-core system with 128 memory request buffer. No complex operations, divisions, not on the critical path. Scheduler makes a decision on only every DRAM cycle. Okay, let's talk about system software support a little bit. So how do you actually make this more flexible? How do you enable the operating system to convey the priority level of each thread to the controller? Basically, there's an interface to be able to do that. You provide levels of priority, highest to lowest priority, and the controller enforces priorities in 2 ways. First, it marks the request from a thread with priority X only every X batch, and that, by nature, ensures that a thread that has priority level that's high, level 1, is always marked every batch. It gets into more batches, basically. Within a batch, a higher priority threads requests are scheduled first. So that's the idea. So there's also an opportunity for purely opportunistic service. Basically, there's a very special, very low priority level L. Requests from such threads are never marked. If you don't care about them, or you need only purely opportunistic service when the bandwidth is available, you mark them with L, and they're not part of the batch, ever. And there's quantitative analysis in the paper for this, but I'm not going to go through that in detail. So let's talk about evaluation a little bit. What are the benefits of this? So we evaluated this with an in-house simulator that we've developed, which actually led to the basis of a lot of the simulators in my group right now that are open source. And we looked at 4 816 core systems, and you can see the parameters over here. I'm not going to talk about that in detail. The paper has the details, but these are the model DRAM parameters that we have. You basically have 128 entry memory request buffer, 8 banks, that's the row buffer size, and 40 nanoseconds and 80 nanoseconds row hit and row conflict latencies. And we use multi-programmed workloads, and we use a large number of combinations for different workloads. So we compare it to different memory controllers. This is baseline FRF-CFS. As we've discussed, this unfairly penalized threads with low row buffer locality, memory non-intensive threads. If you do first come, first serve, it's the oldest first basically. It gets low DRAM throughput to begin with, and it unfairly penalizes memory non-intensive threads because those threads appear to first come to the memory controller if you have a lot of requests. There's 2 other related works. This is network fair queuing scheduler, which basically applies network fair queuing principles to memory, which doesn't really fit very well because it doesn't take into account the row buffer or the banks. As a result, it equally partitions DRAM bandwidth, and it doesn't consider inherent DRAM performance of each thread. So it unfairly penalized threads with high bandwidth utilization and prioritized threads with bursty excess patterns, as we showed in our micro paper. And this is our own prior work. Basically, the idea over there was to estimate and balance the thread slowdowns relatively when they're run alone. This is good for fairness, but it turns out this unfairly treats threads if your slowdown estimates are inaccurate. And that's actually very difficult to get right. That's those slowdown estimates. We found out that they're not easy to get right. And it also requires complex operations. Like it requires a division, but you could approximate it, but it still adds complexity. So we're going to compare it to all of these works. And this is the major result, basically, in terms of unfairness. This is unfairness as we define it. This is the maximum memory slowdown experienced by any thread in the system divided by the minimum memory slowdown experienced by any thread in the system. Ideally, you would like this to be 1 in a multi-programmed workload, meaning that whenever you go from running this workload alone on the machine and running it together with other workloads, you don't see any slowdown. That's ideal, of course, right? And we'd like to get close to ideal. We cannot get perfectly close to the ideal because we have memory bandwidth limitations. And this is what we get. This lower is better, clearly. So FRF-CFS, first ready, first come, first serve, has very high unfairness, as previous work also showed. First come, first serve is actually better. It has lower unfairness. Network fair queuing is good for the 4-core case, but it becomes worse than first come, first serve as things scale. Stall time fair memory scheduling is the best previous scheduler, as you can see. But PAR-BS actually has better fairness than the best previous scheduler. It's about 8 to 11%, well, 1.11 to 1.0708x on average across many workloads. Okay, fairness improves because we have actually this batching. Batching, we found that it's actually good for fairness. And also, we have this ranking mechanism that improves fairness. So system performance also improves. This is one metric, harmonic mean speed up. Basically, compared to the best previous scheduler, this is the system performance improvement we get. It's about 8% to 5%. Of course, this is very much workload dependent, and the workloads are very different when you look at it, 16-core systems and 4-core systems. And also, this is a more bandwidth limited scenario. So if you actually add more channels, we see more benefits over here. Okay, so that's it basically. That's the idea. So let me summarize. Basically, we've shown that inter-thread interference can destroy each thread's DRAM bank level parallelism, because it's, the memory controller serializes a thread's requests because of this interference, and that reduces system throughput. It also makes techniques that exploit memory level parallelism less effective, like out-of-order execution and run-rate execution. Existing DRAM controllers are unaware of this inter-thread bank level parallelism. So we provided a new approach to fair and high-performance DRAM scheduling that takes this into account and introduces some other ideas. The 2 key principles are batching. Batching of memory requests from different threads eliminates starvation and it allows fair sharing of the DRAM system. And the second principle is parallelism-aware thread ranking. This preserves each thread's bank-level parallelism within the batch. And combined together, we have a high-performance and fair scheduler. It's also flexible and configurable because it supports system-level thread priorities. This way, the operating system can enforce quality of service policies. And PowerBS, we've shown that provides better fairness and system performance than previous DRAM schedulers. And now that we have the bell, that's the end of my talk. Thank you. Any questions? That's a conference talk, basically. And there, you normally put backup slides at the end. So if people ask, actually some person asked that question. And I use the backup slides at that time to discuss basically what happens if you do local versus global. So the question was, what happens if you have multiple memory controllers, right? Do you do a local ranking in each controller, or do you do a global ranking? And we explored those over here. And this is the example from the paper. And that's the end of backup slides. So it's now your turn to analyze. Basically, I've given you this part as a conference talk, but of course, the rest is dependent on the audience. But I'm not going to give that to you. You can look at it in the slides. Okay, so we're done for today. We'll meet next week. And then look for the assignments that you have for papers. If you have any questions, feel free to email us. Okay, thank you.